we are now on to uniform circular motion. So, just thinking, because I think we might be going a little fast. Yeah. Well, how many questions do we have? 1, 2, 3, 4. Oh, we should be fine. Alright. Yeah, so I'll just explain what circular motion is. So we got uniform circular motion. It is an object traveling in a circular path with constant speed. It's said to be undergoing uniform circular motion, so such as the satellite orbiting the Earth. So as you can see here, say you've got like a stick with like a string that like goes out to the edge, and then you know, like when you're a kid and you got a ball on a string and you just like twirl it round and round and round like a helicopter. It's like this. So you've always got that equal force going in, and that velocity is always perpendicular to it going out in that one direction. Okay, so that is constant velocity just heading out in that direction. So now we need to define the concepts of average speed and a period. So velocity for circular motion is defined as 2 times pi by the radius divided by the period. And those are all measured in its respectable units. So velocity is measured in meters per second, and then you have the radius of a circular path. It's measured in meters, so that will be this distance here along the dotted line. And I'll just give you a little legend here. So this is our radius. Obviously you've got the velocity there, and then you've got the period to do one rotation. So it's like to go from here all the way around back to that. That was such a bad drawing, but you get the idea. To do one revolution, to do one rotation, it takes so many seconds. So the object's velocity at any point is directly tangent to the circle. Okay, so the magnitude equal to the distance covered in one complete revolution is divided by the time taken. All right, so the velocity will be higher if less time is taken, or if so it's like you have to have that ratio right between the radius and the time. So say you complete a radius in a very low amount of time, then that means you have a greater velocity. But say your radius may be bigger, but it's taking you just as much time. So say to go in a radius, to go in one revolution where the radius is like a meter, and it takes you 3 seconds to complete it, then, you know, that's like our base, right? But say it takes you 6 seconds the next time round, that means your velocity has decreased because that ratio has then decreased. So the radius and the period here really work hand in hand. So it's just a matter of, make sure you got your units right when you calculate it as well. But you might get some questions where you might get a graph on the external, and they might say, compare the radial distance with the period taken, and you might say, the greater the radius, the more time is taken, or the smaller the time is taken, the greater the velocity. But yeah. And you might do not the research investigation, but an experimental investigation, and you might use circular motion. You might measure the amount of time that it takes to do certain revolutions at different distances, and then you might graph that and compare. It's just an idea, but I saw some people do that. It is quite hard the more distances you do, but it's just to, prove those theories, that the greater the radius, the more time is taken, yada yada yada. It really depends on how you choose to write those predictions. Alright, now we're going to look into a couple more definitions here. So we've got centripetal acceleration and centripetal force. I'm just getting some water. Okay. Yep, so centripetal acceleration, it is calculated using that formula. Acceleration is equal to velocity squared over the radius. And that's the acceleration towards the center. So acceleration, once again, is measured in meters per second squared, whereas velocity is measured in meters per second, and then obviously the radius of the circle is measured in meters. Whereas you've got centripetal force, which is measured by Newton's second law, F equals ma. There must be a net force directed toward the center to cause this acceleration, which is called a centripetal force. So this centripetal force, the formula then becomes mass times velocity squared divided by the radius, the force of which is moving toward the center. So just like how we have here, this is that centripetal force. Yep, so that's measured in newtons. Once again, our velocity is the same, the radius of the circle is the same.